This little plastic part pulls over 1 kilogram of downforce. It glues my robot to the track on every turn. The number one question I get on every line leader video is how did I actually design this thing? And honestly, I don't even know. Well, I'm obviously joking. And today you're getting the whole thing. The geometry that actually matters. The full CAD walkthrough. And the design rules I've tested by breaking things. By the end, you'll be able to design a centrifugal turbine for whatever you're building. Now, there are essentially just 4 numbers that dictate 90% of your turbine's behavior. If you get these right, the rest are just details. 1. The outer diameter. Essentially, the bigger you go, the more airflow you get. However, the bigger you go, the bigger the centrifugal force is, which is something you gotta keep an eye on. Your practical ceiling isn't really a fixed number. It mostly depends on your materials, strength to mass ratio, and the motor RPM. Stronger materials and lower RPM let you go bigger before the blades start falling off. Number 2, the diameter of the air intake. If you go too small, you're choking the turbine. If you go too big, you lose surface area of the turbines. I suggest you start at around 45% of the outer diameter and go tighter if you want more suction or wider if you want more airflow. Number 3, the blade count. Blade count is essentially set by the inner diameter, not the outer diameter. My rule is to go for 1 blade per 2 millimeters of the inner diameter. If you want more suction, go for more blades. If you want more airflow, go for fewer. And lastly, number 4, blade height. I currently run 12 millimeters, roughly 22% of my outer diameter. But here's how I landed on that number. So my first version of the turbine was actually 12 millimeters tall, and I ran the tests. It turned out that I had 1 kilogram of downforce. My logical next move was to just increase the blade height. Well, it turns out at 50 millimeters, the blades just snapped off. And this was mostly because I was using an FDM 3D printer, which uses layers that can easily snap off at the layer lines. So to fix the exploding turbine problem, I just added a retainer ring. However, it turns out the retainer ring completely messed up the airflow, and coupled with the fact that I had to glue the retainer ring together, the whole thing was very unstable. Then when I actually compared the 12mm turbine without the retainer ring with the 15mm turbine with the retainer ring, turns out the 12mm essentially won. It had less vibration, it sounded way healthier, and it actually pulled about the same amount of weight. So in my case, a retainer ring wasn't really the best option. But this is also very geometry specific. Just that a retainer ring didn't really suit my turbine doesn't mean a retainer ring is a bad idea. Now, blade thickness. I personally run 1mm, and it probably would be fine to go thinner. However, I would be sacrificing layer adhesion, which could make the blade snap off again. If you go thicker, you sacrifice the airflow and add spinning mass. Now, blade angle. Steeper blades catch more air per revolution. Shallower blades push more efficiently. It's a trade-off. And remember, all of these dimensions mostly scale. So a 23mm diameter turbine would probably want a 11mm inner diameter and 6mm blade height. Now, one last design rule. The turbine itself is only half of a successful design. The second half is what's around it, because remember, the air leaves the turbine in each direction. So what's around it really matters. If you obstruct the outlet, you're gonna lose performance. A general rule of thumb would be to leave at least 25% of your outer diameter as radial clearance to any obstruction. And if you're still not sure exactly what dimensions you need for your specific build, I made an AI prompt that does the math for you. You tell it what you're making, your requirements, and a couple other things, and it gives you back a full geometry recommendation. Outer diameter, inner diameter, blade count, blade height, manufacturing recommendations, and even how to start testing it. The prompt is on my new Discord, a community for people who actually build robots. Links in the description. It's currently free to join. And that's about it for the design rules. Now let's actually model this thing. Open up a new part and a new sketch on the XY plane, and begin by adding a circle. It should be the dimensions of your outer diameter. Extrude this guy to like about 1.5 millimeters, I suggest. Now we're going to design the blades. But what's important here is that you don't start the next sketch on top of what you've just extruded. You start it from the origin plane, right here. Now, how do you begin? Well, first of all, let's project the geometry of the outside circle. Then we got a couple constructional lines to place. The horizontal one, then we've got the vertical one. You gotta connect to the middle of the circle. Then you mark your inner diameter like this. Then a couple more construction lines are a line like this one. Just leave it unconstrained for now. We're gonna take care of it later. And another line, you gotta connect this one perfectly in the middle of this guy. And we also gotta make it perpendicular. All right, this is already most of the work done. Now you actually gotta put the blades in. And you do that by adding 2 circles that cannot be a construction part. Don't constrain them to anything right now. Just add them as 2 circles, but you gotta connect them at the end of this line. Now pay attention, because here you actually set the blade width and the curvature of the blade. So essentially, if you go for a lower radius of the circle, you get a higher curvature. I hope that makes sense. Now, when it comes to the blade thickness, essentially, if we got 80 here and 82 here, the blade thickness is 1, because that's the difference between the 2 radiuses of the 2 circles. Now, one last important constraint is this one, so that the whole thing actually follows this very important line, because this guy, this is where you set the angle of the blade. And just like that, we're done. Now I will quickly go over how to modify this sketch. Now for this dimension, we can actually set it to this minus 2 times the blade thickness, and we can play with just this guy like that, for example. We can play with the angle as well, and here this essentially sets the length of the blades. This dimension has got to be slightly smaller than your intake diameter, like slightly smaller, just a couple percent. All right, I've played with the dimensions a bit. Set this to 60, the angle to 22, and the inner diameter to 22 as well. Now, how do you actually extrude this guy? Well, because we don't have a closed sketch, right? So you add this guy here. It cannot be construction, and it has to be perpendicular to this guy. And now you've just finished your blade, and you pretty much extrude just this part like that. Now the overall shape of this blade looks pretty decent already, but it's dull, so we gotta make it slightly sharper. I suggest you just go for chamfers right here. And just like that, with a couple chamfers and fillets, our blade actually looks like it. Now you just go for a circular pattern. You select pretty much everything and you go for this. For this blade, I will go for 11, and this should look decent. All right, we've got ourselves a turbine. Last thing I didn't do here is the motor mount, and this is intentional because for my motor it's just an M5 screw, but I've seen for my friends' motors it could be 4 screws even, so it is really selective. But yeah, it's downhill from there. You just go for a sketch here. Yeah, I guess it would probably look something like that. And now lastly, what's pretty good to add are these fillets that will make the blade stick even better. These improve layer adhesion, and I really advise to use them, especially if you're pre-printing. Alright, now I've colored it, and honestly it looks pretty good. And it only took me like 10 minutes to make it, so there really are no excuses. Congratulations on your new turbine. Now I've got a quick tip for you if you're going the FDM route, which is what I'm currently using for line leader. The single most important thing that decides whether you get a working turbine is balancing layer adhesion with print quality. Both are mostly controlled by one setting: temperature. The higher the temperature, the better the layer adhesion and the stronger the blades. The lower the temperature, the better detail and smoother airflow you get. So you gotta balance in between. My settings are already dialed in. You'll find them on my new Discord. FDM isn't your only option though. There's an absurd amount of ways you can manufacture this. SLA, SLS, MJF, CNC in metal, CNC in plastic. Every combination has different trade-offs in stiffness, surface finish, durability, and cost. I had this exact same turbine made in 5 processes so I can compare them head to head. Full performance test, downforce, failure point, and much more in the next video. Drop a comment which one you think wins, and subscribe so you don't miss it.